Good morning everybody. Welcome to the final lecture of module 1 on this MOOC course Smart Materials and Intelligent System Design. In the last particular lecture, we have talked about active smart polymers, and also I have touched the issues on classifications of electroactive polymers, which is a special group among these active smart polymer, and there if you remember we have mostly focused on IPMCs, ionic polymer matrix composite. Now, the reason behind developing these kinds of active polymeric systems was, I was telling that the inspiration was from the muscles, okay, so that you can get a large deformation in the system. However, also we have noted down that in polymers, even though you can get large deformation, you are not going to get large force out of the system. So, this kind of active polymers will give you large deformation, but it will give you low blocking force. Now, already I have once told you about this concept of free strain and blocking force. If you remember that if we consider this as a strain versus force of an actuator, then when it is freely straining at that point, it is actually the maximum point maximum strain that you can get from the system. And on the other hand, this is the point which we call it as the blocking force, where the strain is 0, but you are getting maximum force by stopping the actuator to deform at all. So, that actuator will be giving you the force. Now, this force naturally depends on the one of the parameters is the modulus of elasticity. So, because these polymers are having low elastic modulus, so they will be giving us low blocking force. Now, that is where we will see today that if we use not these polymers, but metallic alloys, for example, nickel titanium alloys mostly used, then you will see that this modulus of elasticity will be much higher, and as a result the blocking force will be much higher. But of course, somewhere there is a compromise that the free strain for such cases will be lower. So, those are the group of materials that I will be discussing today, and that is given a common name which is called shape memory alloys. What I will be talking about is what is shape memory effect first of all, and then the metallic alloys that show such shape memory effect. We will also talk about couple of interesting properties like one-way shape memory effect, pseudo-elasticity and two-way shape memory effect, and finally, I will show you some applications of these shape memory alloy actuators. So, let us begin with that. What is this shape memory effect? Now, many of you might have seen this movie, for example, Terminator 2, which actually amplifies the situation where the robot, even if you melt it down, the moment it is getting cooled, it actually gets back its original shape. So, that is too much of a science fiction, but indeed materials, certain materials it is found that they can actually remember their parent state shape, and that is that happens particularly for certain group of metallic alloys. Okay. So, this parent state is generally with respect to high temperature, and whatever you do with this metallic alloy at the low temperature, the moment you take it back to the high temperature, it will get back to the parent shape, because it can recover the large deformations that are imparted at a low temperature. And we will see later on that it actually happens because of a very regular crystal structure. Most of the times it is a body centered BCC structure that it actually attains at a high temperature. This recovery strengths imparted to the material at a lower temperature, and which is actually later on regained by heating, this entire phenomena is actually called the shape memory effect. So, we will see that how step by step we can carry out the deformation and then recovery of the material. The effect was first observed in gold cadmium alloy in 1932, but gold cadmium is a very expensive alloy. So, you cannot use it for day to day applications, neither it shows very large amount of this shape memory effect. It was found out later on that there are 3 candidates, the 2 ternary alloys copper, zinc and aluminum, and copper, aluminum, nickel, they show this effect, and also one binary alloy, that is nickel titanium, they also very interestingly show this effect of shape memory in it. And once again these things are discovered, particularly the nickel titanium so on, at the Naval Ordnance Laboratory of USA, and hence whenever we say this product, we actually refer it as nitinol, that NOL part is the Naval Ordnance Laboratory abbreviation that is added with it. Now, what is the competitive advantage of SMA? Why should we go for this new material? If you look at it, that from the actuation stress point of view, piezoelectric material was having only about 0.001 meganewton meter per kg specific actuation stress, that means per unit weight. In that same tone, if you actually check with the human muscle, it is slightly better, it means about 5 times better than PZT. However, this SMA is actually several orders of magnitude higher. So, with the same weight you can get much larger actuation stress from the SMA. So, which means it is a it is possibly a much higher level, something like 100 times more powerful than these other materials. So, that is how you can have a very good use of such materials in applications like robotics. Well, in terms of the strain also, if you look at it, piezoelectric material shows very small strain, human muscle relatively shows a larger strain, but SMA shows a strain of around 0.1. So, it is not very high in terms of strain, and the 0.1 also is maximum, we call it as 1000 parts per million, okay, 10,000 parts per million, but this is maximum. Generally what we get is something of the range of 3 to 5,000 ppm. So, actuation strain is not as high as a human muscle, but certainly it is higher than piezoelectric material. Now, when we are talking about shape memory effects, there are 2 different types of shape memory effects. One is called one way shape memory effect and another is called two way effect. In fact, it is the one way effect which is more related to the material property, and two way effect is something that comes through the training of the material. So, in the one way effect, what happens is that material remembers the shape only at its parent state, and that parent state we will be referring it as austenite phase, which is a high temperature phase. But in the two way effect, the material will remember its shape both at austenite phase, that is high temperature phase, as well as at low temperature phase, that is martensite phase. So, austenite phase is high temperature and low temperature is martensite phase, and the material will remember both the shapes. If it happens, if you give proper training, then only you will see the two way effect. How do we manufacture such SMA wires? Well, you can see that the basic composition is very simple, nickel and titanium, but in order to have this crystal structure which will allow the twining, it is to be very pure. So, and also you have to do it at a high temperature, mixing nickel and titanium. So, generally we use vacuum arc melting or induction melting process, and we have to take this in vacuum, so that we can take care of impurities, you can reduce it to a minimum, oxides to a minimum. So, at very high temperature in vacuum, we melt nickel and titanium, mix it together, and then we get the ingot, which we later on draw into mostly wire forms. but today it is also available in thin strips, and people are also talking about porous SMAs, which has some advantage in terms of quick temperature dissipation. We were talking about the parent phase or the austenite phase and the martensite phase, and each phase has its own typical crystal structure. At the austenite phase, that is at the high energy phase, high temperature phase also, there the crystal structure will be body centered cubic or BCC structure, and it is a cubic crystal structure, as you can see that in this unit cell all these are of same size. So, it is perfectly cubic structure. Now, the moment I actually reduce the temperature, then this changes to face centered cubic system, and so from the body centered the crystal structure becomes face centered cubic, and further many times it actually changes from cubic system to rhombic systems in terms of the crystal shape, for example. Now, so these are the two. So, BCC at high temperature phase or austenite phase and FCC at low temperature phase or martensite phase we have to keep in our mind. Now, let us see at the low temperature phase how it would behave. Well, if I reduce the temperature from BCC to FCC, we generally do not see an appreciable change in terms of the original shape or the size of the system. Why is it that we do not see? It is because that even though it goes from BCC to FCC, but the crystals very nicely create a fold. You can see a fold here, you can see a fold here, a fold here. So, these folds actually take care of that expansion that could have happened in the or contractions that could have happened in the system. So, that is why there is no shape change that you will see if you cool a system from austenite phase to martensite phase, and this particular martensite phase is called twinned martensite phase. Now, so when we are applying stress, so far we are only applying temperature to bring it down to twinned martensite phase. So, let us say at low temperature we are somewhere here where we are at the twinned martensite phase, and now I am increasing the stress. As I am increasing the stress, there is a sigma stress critical, beyond which this twinned martensite state will actually these folds will vanish, the crystals will layer, these layers will start to actually slide, each crystal layer will slide, and then you are going to get this kind of a rhombic shape. So, this is your detwinned martensite phase. So, here sigma SCR starting of the twinned martensite phase, and then sigma FCR, that is finishing stress at which complete detwining has taken place. So, you have to even though this looks like plastic deformation, but this is essentially crystal twining that is taking place in the system. Now, once it is in the fully detwined shape, so it is here again if I increase the stress, it will behave again like a elastic region. Okay. So, the same way, and finally, once the stress is beyond a certain level, there will be the onset of slips, and then the plastic deformation and the failure will take place in the system. So, the initial large deformation that you will see is not because of plastic deformation, but because of these twining detwining to twining, this transformation that is happening in the system. So, twining to detwining or detwining to twining. So, that is what is the low temperature stress strain behavior in the system when you are only in the martensite regime. Now, what happens if I look at it with respect to temperature? Well, if you take a sample at a very low temperature, let us say, we expect it to be here somewhere at a completely martensite phase. and what Martensite phase? If there is no other stress etc., then it is supposed to be at the twined Martensite phase. As I am increasing the temperature gradually, okay, so we will come to a point which is called austenite start. So far it is at the twined Martensite state, and also this is having FCC structure, as we have already discussed. At S, what will happen? That some of these crystals will start to get transformed to BCC structure. So, now this FCC to BCC transformation is happening, but not fully, only some crystals. As I am increasing the heat further, somewhere at AF I get full transformation to austenite. So, all BCC I will be getting at this stage, all BCC. So, that is everything has been transformed from FCC to BCC, austenite finish, I go to the parent shape of the system. What happens if I again cool the system? So, this is 100% austenite. If I cool it again at a particular temperature MS, the BCC will start to get transformed to FCC. So, now BCC will start to get transformed, not all of them, but just start the process. And as I reduce the temperature further, it will reach a point when Martensite finish will come, and it will complete this, and it will be completely Martensite, and it will be having completely FCC structure. So, that is a temperature dependent behavior. Now, look at it, that when this is happening, this MS and MF, they are not actually coming at the same point, neither AS and AF. So, there is a hysteresis that is always present in the system. Now, that hysteresis is something which we will see later on, that in terms of stress we can actually exploit it as pseudo-elasticity. In terms of temperature, this hysteresis for an actuator is not very good, the narrower it is, the better is the system. Now, let us look into the one way shape memory effect just once again, because it is little bit complex. So, let us see that I have taken a beam here and I am bending the beam here, I am giving a deformation, bending the beam, and this is at its original shape, that is at austenite high temperature. Now, I am simply cooling this system. What will happen? I told you that there will be no change of shape. So, if I cool it, there will be no change of shape, length is still the same, which means here also in the bent case there is no change of shape, but only it will get converted from austenite to twined Martensite phase. Now, if I apply load, so I am deforming, I am applying load, and then if I apply the load, what will happen is that there will be a change of shape that will happen to the system, and that means this twined Martensite is going in the Martensite phase in the detwined shape. Now, again if I heat it up beyond a certain austenite finish, of course, beyond austenite finish we will get 100% recovery. So, you will get back the original shape just like this shape. In this case also you will get back the original shape just like this shape. Okay. So, that is the one way shape memory effect, and how people got excited about it is phenomenal, that they first thought of NASA that let us make an antenna out of the shape memory alloy wires, and then let us at the Martensite stage, low temperature stage, let us deform it, because at the Martensite stage you can deform it. Okay. So, you squeeze it, that whole antenna you can make it at the austenite phase, and then you squeeze it, and you can make a small roll out of it. Now, the moment you deploy it in the space, you increase the temperature, it goes to austenite phase and you get the full antenna back. So, that was how first applications were actually envisaged of this one way shape memory effect. Now, what if so far we have not done two things together? What if I do both the things together, temperature and stress? Okay. So, there are three parameters here in this system, stress and temperature and strain. Okay. Let us say we start from a situation 1, okay, and where this whole thing is supposed to be at the twined Martensite phase. I am increasing the load. So, detwining is happening and I will be reaching 2. If I increase the load further, the material would have failed, but I do not want to do it. I am reducing the load now. If I reduce the load, it will not actually get back to its original shape, because there is this detwining to twining, that load release will only bring it back to the partial, the elastic part of the recovery. Then I heat it up. As I heat it up, it actually goes to 0.4, and here full recovery has taken place, full recovery of the shape. And then if I cool it up, then what will happen? It will go back to its Martensite state, that is here we should say that the twined Martensite state here, and that would not mean there will be any more change of strain. Strain is 0, okay, but only that it will get converted from the austenite to the twined Martensite phase. So, that is the whole diagram we have to keep in our mind. Now, there is something which is called pseudo-elasticity. Now, the way the whole thing happens is that in the austenite phase, that is at the high temperature phase, if without changing the temperature, if I only apply stress, then what happens is that this austenite phase can get converted to the detwined Martensite phase, and this procedure. Okay. So, directly, that means you are not coming to twined Martensite phase, but directly between austenite to detwined Martensite phase transformation, this has lot of hysteresis in it, and that is why the pseudo-elasticity, that means it is not perfectly elastic, but it is because of a stress induced phase transformation, and neither it is plastic. So, that is why it is pseudo elastic, and this involves large hysteresis, and that is used for structural damping due to large hysteresis in this particular transformation process. So, that is pseudo elasticity, which we will show later on that can be used in structural damping. In fact, this is what is this stress induced transformation diagram. You can see that you are at the austenite phase, increasing the stress, and it is going to directly to the detwined Martensite phase. So, here this detwining is complete, detwined Martensite phase. There is no change of temperature, remember, and then as I am reducing the load, okay, I will come back to the austenite state here, and this process has a full hysteresis that you can see. Now, what if I do not take it to complete detwined Martensite phase? That is possible. In this case, it will be partial pseudo elasticity, as you can see that you are going partially and coming back, and there will be some amount of recovery strain that will be there in the system. So, complete pseudo elasticity will can bring it back to the 0 strain condition, but partial pseudo elasticity will have some amount of remnant strain in the system. Now, what are the commercial applications of this effect? Well, the first effect actually came from one of the aircraft applications by Raychem Corporation, and this is known as cryocon. So, what they have done in this case is that this is used for joining tubes in aerospace systems. So, initially the shape will be oval ring of SMA, and that will be set at the Martensite phase, oval ring, okay. And then you can easily join the two system at that shape. Let us say you design it in that manner, and this is happening when it is cryo cooled, which means it is fully at the Martensite phase. Now, you remove that cryogenic condition. So, it will go back to its memorized shape, and the memorized shape is actually a circular ring. Okay. So, the moment that happens, then there is a tightening, because it is squeezing inside the tube and joins the system. So, as a result you can fit it at the cryogenic condition and get a complete beautiful connectivity between the system. That was the first effect using one way SME. Now, one way SME remembers only one shape, that is the high temperature shape, but if you actually reduce the temperature, then this memory gets erased. However, if you do it in a cyclic manner, then what will happen, that is what we call the training, then it will remember both the high and the low temperature shape, and that is in some applications very much useful, that you get both high as well as the low temperature shape. Say for example, you have this as the original shape when temperature is less than Martensite finish. You are plastically deforming the system. Okay. So, you are in that bend shape. Now, you are heating it up, but only partially you are recovering. Okay. So, you are coming back to the austenite phase, and then from this stage, if I cool it, temperature is now less than MF. Okay. I am getting this particular shape, and I have to repeat in this cycle continuously. If I do it, then it will be trained, and in that case, whenever every time you will actually cool it, you will get this shape. So, not only you will get the austenite shape, but also you will get the Martensite shape every time, and that is what is the two-way shape memory effect that you will get in the system. Now, there are lot of applications of these. For example, the two-way effects can be used for control of aerodynamic surfaces. So, that you can bend it in a manner that it goes from one shape to another shape. So, you can use it for flapping of wings, for example. Then you can use it for as micro coils for vibration isolation, you can use this system. Grasping by robotic fingers, people have tried it. Space exploration like rock splitting, nitinol filters, deployment of solar array hinges. There are many such space applications that are thought of by using this effect. Some of the very specific effects that we are doing in laboratories are, for example, we have two series of SMA wires, one below and one one top, one below of a cantilever beam, and then by actuating each one of them. So, like if you consider that this one you just have time versus current, you pass it in a manner that it is like this. So, at a repeated cycle you are doing it, and so this is I1, let us say for this one I1, and let us say for this one current is I2. So, if I plot I2 versus t, I just do it just the reverse manner, that means like this. So, by repeatedly periodically heating up the top and the bottom, you can actually generate, if you look at time versus displacement of any particular point, let us say I am trying to plot the x, the displacement of this point, I would be actually getting this kind of a deflection in the system. So, that is how you can generate vibration in a system. People have used it for the chevron using SMA actuators by Boeing, and what they have done is that if you look at it, that this part is actually jagged. Okay. So, at the beginning, when you are the taking off is happening, at that time this part is jagged, and as the heat increases, so this jaggedness actually helps in terms of attenuation. Okay. So, the sound will be much less. This you will see in Dreamliner, all Dreamliners, if you look at it, you will see that this technology is there. Now, as the temperature is increasing, the aircraft is going at the high altitude, you do not, the sound does not matter anymore, and this the temperature will make it actually flat. So, this will become flatter. So, that you get more fuel efficiency from the system. So, that is how this particular system was very cleverly designed. There there is also another example of amplified SMA actuator to further amplify. So, let us say this is the SMA at this core, and as you are shortening, it is like these 2 points where you are getting a mechanical amplification of the system by using arch type of a mechanism. So, thus you can actually further amplify the deformation. One last use that I want to talk about is actually, so far I have only talked about SMA based actuators, but now I want to just show one last slide on SMA based sensor. So, in this case what you can do is that suppose you have a micro switch tip and you have SMA wires, okay, and you have a system which is actually having two such micro switches, as you can see A and B. and you have 2 point touching 2 parts of the conductive strips. Now, if this system rotates, what happens? That there are certain times when these 2 stylus will be over 2 of these conductive strips. So, whenever they will be at the 2 conductive strips, there will be current which will be flowing, and as the current will be flowing, then you will be getting the heating here, and this switch that we have here, that switch will be actually pressed. So, that means the current will be flowing on. The next moment, if one of them goes here, that means the current is not there. So, it will once again lift up. So, you will be able to see this kind of a current flowing, and again no current, current flowing, no current situation. Now, if you have 2 such switches with a phase lag between them, then there is a phase difference that you are getting between 2 adjacent switches. So, by measuring this phase delay, you should be able to say that how fast the angular rotation omega is taking place in this disc, and by integrating that you should be also able to say how much of angular deformation has taken place. So, this can be used for sensing of angular sensing by using SMA. So, briefly I have told you that what is the shape memory effect. I have told you about 3 shape memory effects, one way, two way and pseudo elasticity, and I have talked about the shape memory actuators and the shape memory based sensors in this particular overview. In the next lecture, I will talk about introduction to composites. Thank you.